with example number 2, and I'm going to try to speed these up a little bit. I think most of you are fairly comfortable with finding reactions. So we have a little simple frame here that has a pin at A and a roller at B. And so when I draw my free body diagram, it's going to show my pin at A and my roller at B. And I want you all to take note. This is not a two-force member. Okay, this is one member that happens to have a 45-degree angle in the middle of it. So this actually has a load on it, not two-force. Remember, a two-force member is something that's pinned on both ends. So if B was actually a pinned reaction and I had a pin and had A to, let's call that E, and E to B, then yes, we could call this a two-force member, and we would know that the X and Y components would have to follow the same direction as that two-force member in terms of geometry, but that's not what we have. So as I go through here, I'm going to draw my free body diagram. Yours should look the same. I like to have my geometry on my free body diagram. So I note that this is 45 degrees. It's 6 meters long, so I can easily find the X and the Y components of those distances. And I know because this is 45, my X and the Y have to be the same magnitude. And we got 4.24 meters. So I chose to sum the moments about A. You could have summed the moments about B because, you know, we can look forward, AX equals 0. So you could solve for AX first equals 0. There's nothing in the X direction. This is not a two-force member, so we don't have a vector passing through it in the same direction that has the X and Y components. This is all one member. That's why I picked this problem. So I summed the forces about A, and I got 8.48 kilonewtons up. Again, we always show direction when we find a reaction. I summed forces in the X direction, got 0. I summed forces in the Y direction, and I got that AY is 3.52 kilonewtons. Now, I always say in statics, you should never have a wrong answer. If I wanted to check my work, I could go back and sum the moments about point B, and they should still equal 0. And if I did that, you guys see everything? I'm going to back this up a little bit. I would have a negative 12 kilonewtons from my load times 4.24. Oh, I'm going about A again. Got to pay attention to what I'm doing. I'm going to go about B this time. So if I'm looking at B and I sum the moments about B, I'm going to have 12 kilonewtons times 3 meters. Okay, I'm going to look back up here, note that AX is 0. We don't have any forces in the X direction. And I want to find AY. So I'm going to have a minus AY times 6 plus 4.24 is 10.24 meters. And I know the sum of my moments about B has to equal 0. And I will again find that AY is 3.52 kilonewtons positive, so going up. And I can say check. Okay, it works. So the next thing we want to do is let's go ahead and work with at D. We want to find the internal forces at D. So I'm going to slide this back up. When I look at my overall, I know that when I'm finding internal forces, I either have to make a cut where I show everything on the left, or I can show everything on the right. Okay, everything on the left. So I would have a BY here plus this, or I could have, I guess that was AY, a BY in my internals. This looks a whole lot easier than this, simply because I don't have extra distances. So I'm going to draw this part of my beam. Again, I don't want to use this free body diagram because if I do, I might make the mistake of saying that there's no other forces acting on this beam when in fact there is a uniform load. So forget this right now, go here. Okay, draw your free body diagrams. So I have BY is 8.48 kilonewtons. I do have a uniform load, and I know the area is 3 times 6, so I have 6 kilonewtons, internal positive, internal positive, internal positive. We always assume positive behavior. I can sum forces X. They have to equal 0. I have a negative N equals 0. Again, it's showing tension on this member, and tension is positive behaviorally. When I'm using the tools in my toolbox, my equilibrium equations, I have to go by what direction I'm calling positive to sum my forces. This N is negative according to my rule of right is positive. Okay, so I can say normal equals 0. Do I have to tell you that even if I can see there's no X forces? Yes, you do, because a normal force could develop. Then we're going to sum forces in the Y direction. Again, my equilibrium tool of summing my forces, up is positive. It just happens to coincide with my behavior. So I have shear minus 6 kilonewtons plus 8.48 kilonewtons equals 0. That should be a plus. Positive, negative, positive. So my shear equals negative 8.48. Good grief. Negative 8.48 kilonewtons plus 6 kilonewtons. And I get that my shear is negative. And what did I get from my shear? Negative 2.48 kilonewtons. Okay. And again, we're showing a negative because it would need to be going counterclockwise in order for equilibrium of this to exist. I'm also going to go back and note that this is 1.5 meters and 1.5 meters. That will be important when I'm finding my internal moment. So now we're going to sum our moments about that point. And again, I'm super quirky. I have a system. I'm going to sum about my cut. And I notice that I have a moment that could develop internally, so I have to include it. It's happening right here at this point. Minus 6 kilonewtons times 1.5 meters plus 8.48 kilonewtons times 3 meters, and all of this equals 0. So my moment equals positive 6 kilonewtons times 1.5 meters minus 8.48 times 3. My moment equals a negative, see if I can calculate that, 8.48, 3 times 6 center, 1.5 times, plus I get negative 16.44, what are my units? Kilonewton meters. Okay, again, I call it negative, and that lets me know when I'm doing design work. Negative moment gives me a rainbow looking curvature, unhappy face, unhappy, like no smile, so that I know I have tension top and compression in the bottom. Okay, so now let's move on to at C. I want you all to look at C, and I want you all to pause the video and draw your shear moment diagram. And I'm going to move my paper so that I have more space. I'm going to actually turn it over. So hold on. Okay, sorry about that. I'm just trying to conserve paper while I'm at home. And anyways. So at C, when you look at that free body diagram, you can come from the left to the right or the right to the left, and I'm going to choose to go from the left to the right because it just has less mess and less distances. Again, when I draw my internal, normal is always perpendicular to my surface, shear is always parallel, bending moment. We are coming from left to right, so I am showing you positive notation, clockwise rotation, tension, smiley face curvature. When I come back at my reaction, I note that I don't have an X component. If I did, I would just have to make sure I dealt with that. But I do have a Y component, and my Y component is, sorry, I have to go back and look, 3.52. Yep, 3.52 kilonewtons. Okay, so there's two ways I can approach this. I am going to rotate my X and Y so that I don't have to rotate both a normal and shear into the X and Y of my force, rotating it. It's easier to rotate it here. Okay, and I have two ways that I could approach this problem. I could, because it's 45 degrees, it's going to end up showing you a lot more grace. I could say this is a right triangle, and I have a force of 3.52 that's coming along this plane, so I know that this angle is 45 degrees. Okay, so when I look at this 45 degrees, then I could call the y component sine of 45. And I could call the x component cosine of 45. Do you guys see that? Okay, if I make a 45-degree angle up here because it's 45, 45, I could call this y direction is going to be 3.52 sine of 45. The x component of my reaction times cosine of 45. That would be the x component in my rotated system. Or the other way I could approach this is I know if I have this system, okay, and if I am rotating from my x-axis to that member at 45 degrees, then I know that I'm also rotating from my y-axis to the new y-axis at 45 degrees. And if I do this method, this is 45 degrees in here, then the y component, so the y component is now 3.52 sine 45, and the x component, oh shoot, guys, I wish I knew how to stop and rewind. Okay, the x component right here, because I'm going here, that's parallel. The x component is now 3.52 sine 45. And the y component, so the y component is 3.52 cosine 45. Now the 45-degree angle, it doesn't make a whole lot of sense, or it doesn't really matter because there's grace shown with 45s, because it doesn't matter if you screw up and call it sine or cosine, you get the same answer. But you need to know how to do this, especially moving forward to your next class when you have members that we need to find internal forces for that don't necessarily fit our x to y normal coordinate system that we use. So I am going to kind of come back here and I'm going to erase this because you guys know I like to erase things. And I'm going to go ahead and actually break this up so that I can find the components in my new coordinate system, my new direction. And I am going to use, it doesn't really matter which one I use, so we can just use this one. So I'm going to have 3.52 sine of 45. And if I'm going up, okay, then I'm going in this direction, 3.52 cosine 45. Because again, I like this system to be as easy for me as possible, And hold on.